Okay, we'll do some more induction practice. First of all, in this video, so we've got a coil. It's got a 8 by 8 centimeter square coil with 300 turns of wire in a magnetic field of 0.75 Teslas, and the angle between the coil and the field is 25 degrees. Now, what we're going to do is we are going to let's turn the coil vertical in 0.14 seconds, and we're going to find the induced, oh, that's a terrible E. We're going to find the induced EMF inside the coil. So we're going to start with that. Okay, so first of all, we've got to find the fluxes and then find the difference, etc., etc. So let's see what we can do here. So let's start with flux number 1. So let's find the flux of the coil right now. So BA cos theta. Of course, we have the B, that's fine. We need the area, it's 8 by 8 centimeters squared. I know that's a tough one for you guys, you know, being some of you guys are even calculus. To find the area of a square could be really hard, but 0.0064 meters squared for our area of R square. So we have that, and we've got the cos theta. Now, of course, the trick, as you guys would call it, is what angle to use. Do you use the 25? Well, let's look at it. Is it closer to minimum flux or maximum flux? Well, the way it's positioned, it's almost flat with the field. That's closer to minimum flux. So what's smaller, the cos of 25 or the cos of 65? Which of those two is smaller? Well, that would be 65. The cos of 65 is smaller because, of course, we don't want the angle between the field and the coil. We want it between the normal and the field. And if that's 25, that's going to be 65. So we want to use the 65 degrees. So if we do that, we can find out the initial flux in the coil. And that will give me 0.00203 Webers going through it right now. Okay, so now I'm going to find my new flux, so BA cos theta. Now, if I turn that coil vertical with the field, that is maximum flux. So I know that cos theta is going to be equal to 1, don't even have to worry about it. So I can then find my new flux, which is going to be higher than what I actually started with because we're gaining flux. So if I do that calculation, we will get a new flux of 0.0048 Webers. Okay, so remember, it's not about how much flux you have, it's about the change in flux. So if I take those two, I can find my change in flux by subtracting the two. And if I do that, I will have a change in flux of around 0.00277 Webers. All right, now that I have my change in flux, I can go to my expression. So we've got induced EMF is equal to negative N change in flux divided by change in time. All right, I got my N value right there. I got my 300. I've got my change in flux right there. And my change in T is the 0.14. So I can put them all together. This time my answer will end up being negative, and I will have my induced EMF. There's no negatives to cancel, so negative 5. Well, that's a terrible 5. Get rid of that. Negative 5.9 volts, I believe, should be the induced EMF in that coil. Okay, so once again, just find the quantities, piece them together. The maximizing, minimizing is the way I like to look at which angles to use. I just find that a lot easier than trying to figure out geometry, which can be kind of complicated sometimes, but I just like to do it that way. Okay, so there's another example. All right, so let's see if we can work with this a little bit more in terms of what Lenz did. We've mentioned Lenz before, and Lenz had a lot to do with mathematizing the Faraday's law type thing as well as other things. But Faraday also figured out something else. And I'm just going to go back to something I drew a couple videos ago where we had that piece of iron looked like this. Remember we had two sets of wires, one set of wires there, one set of wires on here. Basically something like this, what we had. Okay. Now in the previous video we had the first side over here on the left hand side. Okay, that was our source. Now of course that source made an EMF, it made a current, which made a magnetic field inside of the iron, which then went to the second coil. And of course, the second coil goes and makes an induced EMF, it makes an induced current, blah, blah, blah. But if that second coil makes a current, and there's another current going through these wires over here, that wire is going to produce its own magnetic field. And it goes through these loops over here. Not only does that first side make a magnetic field, but so does the second side. And the second side will make a secondary magnetic field. There isn't just one magnetic field, there's two. There's two EMFs, there's two currents, there's also two magnetic fields. And this is where Lenz really kicked in. And what Lenz sort of figured out is that second current and stuff like that makes another magnetic field. Okay, so we've got two of everything. And what's interesting is the change in magnetic field on the second side actually basically fights the change in magnetic field in the first side. And you can say flux as well if you want to. It doesn't make any difference. But basically, one will fight the other. It'll try and undo what was done. They actually try and cancel each other out. These two changes, these guys try to cancel out. It basically tries to undo what's been done, all right? And this is where Lenz's law kicks in for induction a lot more. Is you don't just have one of the magnetic fields, you've got two. You've got two EMFs, you've got two currents, you also end up with two magnetic fields, and they try to cancel out. They try and sort of do the opposite or fight the change and stuff like that. It's sort of like, one of my favorite analogies for this is sort of like a 5-year-old. If you tell a 5-year-old not to do something, pretty much guaranteed they will do it, and they'll do the opposite. If you try and take something away, they'll try and take it back. If you try and give them something they don't want, they'll push it away. They always try and do the opposite, and Lenz's law is an awful lot like that, where you tell a 5-year-old to do something or not to do something, they'll do the exact opposite, okay? Not only 5-year-olds, but also, like teenage boys, but whatever. Anyway, so this is where Lenz's law kicks in, and we are going to practice that a little bit. Now, to practice that, we are going to actually use a sheet that's posted on your class website, and it'll make things a lot easier, and I can sort of show you how this type of thing actually works. Okay, so this sheet is in your posted on your class website, so if you can follow along and go with the sheet, it'll make things a lot easier. But here we got some different scenarios, and we're going to look at some electromagnetic induction or Lenz's law. So in the first situation here, we have a circular coil with a magnetic field going through it. I don't know why it's purple, but whatever, it's purple. And what you're going to do is remove the coil. So if you remove the coil, obviously the field is going to change. The flux is going to change. You're going to get an induced EMF. So if we remove the coil, inside the coil, it is going to lose the magnetic field that's inside of it. It's going to lose X's. And when that happens, it's going to try and compensate for this. It's going to do the exact opposite. So in order to actually compensate for this, while you pull out the coil, it is going to make X's to try and undo what was done. It's trying to compensate. So the induced magnetic field inside of the coil is going to be an X. Okay, you took away the X's by removing the coil, it's going to make its own. And if you'd actually shove the coil back in, you'd actually get the opposite. Okay, now if that is the induced magnetic field would be an X, this is where you can use your right-hand rule, number 1, to figure out which way the induced current would go. And my thumb would be pointing down, and my induced current would be going around in that direction. Okay, so this is sort of how this works. Okay, so let's take something similar. We're going to put the coil in to a magnetic field of dots. So here it is going to gain magnetic dots. All right, so now the coil is going to make its own magnetic field to try and cancel this out and compensate. You gave it dots, so what is it going to do? Now it can't lose dots, it doesn't have any dots to lose. So what it's actually going to do is it's actually going to make X's in order to try and cancel it out. Here it made X's to make up what was lost. Here it's going to make X's to try and cancel it. You're giving it dots, so it's going to make X's to cancel it out. So once again, the induced magnetic field would be an X, and the induced current would go in the sort of like the clockwise direction, the same as the first one. So again, coils and stuff like that typically make things to either make up what was lost or try and cancel out what is being given. Okay, so let's go to another scenario here. All right, so here we got a wire with a current going through it. So the first thing I'm going to do is I'm going to draw the magnetic field for the wire. And using my right-hand rule, I would have dots on this side, and I would have X's on this side for my wire. I'm going to change my color here a little bit. Change the size. I'll change the size. I like blue. All right. So if you turn off the current, right now that coil's got dots in it. If you turn off the current, it is going to lose. It's going to lose dots. So since it's going to lose dots, it is going to make dots in order to get back what was lost. So the induced magnetic field would be a dot this time. And using a right-hand rule or just reverse the previous pictures, the induced current would go in that direction. Okay, the next one, you've got a coil sideways here. It's got nothing going through it. There's no flux through that coil whatsoever. And then you turn it to look like the picture on the right. So now you've given it magnetic field. So what has happened is it has gained dots. So you gave it dots. So it's going to try and cancel it out. It is going to do that. It's going to make X's to cancel it out. So the induced magnetic field would be an X, and the current that's induced would go in this direction. Okay, so again, it's about making field to either cancel what's given or to make up what's lost. All right, one more scenario we're going to look at. Okay, all right, so here we have a magnet and a solenoid. You got a coil, and we insert the magnet. So this is very similar to the simulation I showed you. So right now, the magnetic fields, remember, magnetic fields go from north to south. So if you draw the field like that. So right now there's field inside going towards the right. So if you insert the magnet, obviously the field inside is going to get stronger. So you are going to have more field going towards the right. So to compensate and sort of trying to cancel this out, the coil is going to make a magnetic field to the left. So the induced magnetic field is going to go in the opposite direction. And then you can use your right-hand rule again for circular things. You guys learned in grade 11, worked on again in grade 12. To do that, the induced current would be going up in this direction, going up this side. Okay, and of course, if you'd remove the coil, or remove the magnet from the coil, it would lose field to the right, so it would make field to the right, and everything would get reversed. And remember the simulation I showed you, when I would take the magnet in and out, the induced EMF and current would switch directions depending on which way it was going. So this is just another example of applying Lenz's law to the situation. So again, it's all about the coils and the loops, the solenoids, whatever. If you give it something, it's going to make the opposite. If you take it away, it's going to make the same to try and compensate. And that's the basic idea behind Lenz's law when it's attached to Faraday's law. Okay, so if we go back to this we were looking at before, basically when you induce something or have induction going on, basically coils, loops, or whatever you want to call it, loops make magnetic fields to do one of two things. Either to cancel what is increasing. Okay, let's fix that. To try and cancel off what is increasing or given to it. Okay, so if it's getting more X's, it's going to make dots to cancel it out. Okay, so it's going to make magnetic fields to cancel out what is being increasing or becoming stronger or is being given to it, or it'll make a magnetic field to make up what is lost. Okay, so if it's losing dots, it's going to make dots to compensate. If it's losing field up, it's going to make some up to compensate. So it's all about canceling what's being given or making up what's being lost. And that's the basic idea behind Lenz's work and Lenz's law and that type of stuff. Okay, and there's some really, really cool things I could show you about this. Really cool demos in my lab if I could, but unfortunately we are remote learning, so I am not quite able to show you some cool demos. But that's, if you look up Lenz's law demos like on YouTube, you can actually find some pretty cool stuff, especially with magnets falling in conducting tubes and stuff like that. Okay, but we will practice some more with Faraday and Lenz's law in the next video, and apply induction after that as well.